Swayam Prabha. Digital India. Educated India.
Listen. So you see, so what is the so you see, let's continue. See, we are trying to understand torsion, okay, and that's because we are trying to understand space curves. The broad idea is that we want to get an analog of the following statement, namely, for a plane curve, uh, the sine curvature determines the plane curve, and it determines up to rigid motions, okay, and you want to make a similar statement for space curves, and in that case, in the case of space curves, you not only have curvature, uh, you have also torsion, okay. So what happens is that you have the statement that space curves are completely determined by their curvature and torsion, okay, and when you say completely determined, this is up to a rigid motion, okay. So that is a statement, all right. But there are a few differences. In the case of a plane curve, you have this thing called sine curvature, that is, you put a sine to the curvature, and this sine curvature is related to the signed normal, okay, which is the usual tangent. You take the unit tangent vector and rotate it by 90 degrees anti-clockwise, and you have to worry about the sine normal and the sine curvature, okay. But the big deal is that this sine of the curvature is given so that the sine normal, you have to adjust the position of the sine normal with respect to the geometric normal, which always points towards the center of curvature, okay. But this sine adjustment that we did, we saw that it is not just an adjustment. Analytically, the sine curvature is important because that is the rate of change of the turning angle, okay. And studying this turning angle is what gave us many things. It gave us the Frenet-Serret relations, okay, and which are the most important relations which give the dynamics of a curve or a particle moving on the curve, okay. Now and of course the curvature itself is the rate of change of the turning angle. We also have that interpretation. What is the importance of this interpretation? If you integrate the curvature with respect to arc length, you are actually integrating rate of change of turning angle with respect to arc length, again with respect to arc length, okay, and that means you will get only net change in turning angle. And this gives you a very important paradigm, which is you integrate curvature, you should get an angle, okay. And one standard example of that is the Hopf-Umlauf-Satz, which says that if you integrate curvature on a simple closed smooth curve, the angle you will get is plus or minus 360 degrees, plus or minus 2 pi radians, okay. And this is a very special, simplest case of the so-called Gauss-Bonnet theorem, okay. Now we want to do all this for space curves, but in the case of space curves, curvature is not alone enough. You need also to bring in torsion, okay. But the difference is that the curvature for a space curve will be unsigned, so it will be only the magnitude of the curvature. The sine is taken care of by the torsion. The torsion will have a sign, and why that is enough is because the Frenet-Serret frame in the case of a space curve is going to be a right-handed frame consisting of the tangent, the normal, okay, the principal normal and the binormal. So if you recall, we had this kind of a picture. So here is so here is your space curve, okay, and it's given by capital gamma of s, where s is, let us say, the arc length, okay. We always take unit speed curves, okay, and because that is the situation in which the Frenet-Serret relations are written, all right. And for a unit speed curve gamma s, parameterized by S, which is the arc length, increasing arc length, okay. Then gamma dot is the tangent vector, and it will be a unit vector because it's unit speed. So you get this tangent unit vector, and it's written as t cap, all right. Then you have what is called the principal normal. So this principal normal is, the way the principal normal is defined is exactly the way, you know, the normal is related to the, you know, the tangent in the case of plane curves. So in the case of plane curves, you see the signed normal is the tangent, it is the derivative of the tangent vector, okay, which is acceleration, divided by the sine curvature, okay. And we imitate this and say that in the case of a unit space curve, we define the principal normal. Now we don't use the word sine normal, okay, we use the word principal normal. And you don't use the sine curvature, but you use the magnitude of the curvature. So the curvature is always non-zero, it's always positive and non-zero, okay. And mind you, you are dividing by that, okay. So the curvature is not zero. And then what you do is that you define the principal normal to be the derivative of the tangent vector, unit tangent, divided by the magnitude of the curvature. And mind you, to define this, I have to divide by the curvature, so the curvature should never vanish, and this is always positive, okay. So again, the point I want you to compare and contrast is that for a plane curve, you don't define curvature at a point where its velocity is 0. So to define the curvature of a plane curve, you need it to be regular, you need the velocity to be non-zero, okay. And similarly, to define the torsion of a space curve, you need its curvature to be non-zero, okay. You have to remember that. So this is how the principal normal is defined. Once you have the tangent direction and the principal normal, you can complete the right-handed triad to get what is called the binormal, and you get a right-handed system. So you get this binormal, okay. It is just that the tangent direction, the unit tangent vector cross with the principal normal vector, that is a binormal, okay. And what is the picture? So the picture is like this. Here is your curve, this is the orientation of the curve, okay. You have this tangent vector, okay, unit tangent vector, which is t cap. Then you have this, which is the unit normal, that is n cap, okay. And then perpendicular to both of them, you have this b cap. This is the binormal, and this t cap, n cap, b cap is a right-handed system. That means, you know, t cap cross n cap is b cap, n cap cross b cap is t cap, and b cap cross t cap is n cap. So this behaves just like I cap, j cap, k cap, which are the unit vectors along standard xyz axis, okay. How they behave under cross products, okay. So there is something, there is some terminology here. So let me tell you, the terminology is that, you know, this, you see this plane which contains the tangent, the unit tangent vector and the unit normal vector. This is the plane which contains the circle of curvature, and it's called the osculating plane. So this blue guy is the osculating plane, okay. And this osculating plane is a special plane. It contains the circle of curvature, and then it also contains the center of curvature, okay. And this principal normal is the geometric normal, all right. Now there is also this normal and the binormal. They also determine a plane, okay, and that plane is called the normal plane, okay. So let me use a different color and show you that. So you see there is also this, so maybe I'll use this. So you see this green thing is the normal, okay, and then you have this thing, this is the binormal again here, okay, and then there is a plane like this. That plane is the plane which contains both the normal and the binormal. So this plane is called the normal plane, okay. And Finally, there is one more plane left, which is the plane containing the unit tangent and the binormal. This is called the rectifying plane. Okay, so let me put it in another color. Let me try to see whether I can get. Oh, so I can use this. So there is this. This is the tangent, and this is the binormal. Then I have one more plane like this, and this plane is the rectifying plane. Okay, basically these are the analogues of xy plane, yz plane, and zx plane. If you had taken I cap, j cap, k cap as unit vectors along positive x, y, z directions. Okay, so to repeat, the osculating plane contains the unit tangent and the principal normal. It is the plane that contains the circle of curvature and the center of curvature. Okay, then the plane that is determined by the normal and the binormal, that is the normal plane. Then you have one more plane which is determined by the binormal and the unit tangent. Okay, and that is a rectifying plane. Notice that the binormal is also a unit vector because it is a cross product of two unit vectors at right angles to each other. So this binormal is also a unit vector. Okay, and what is happening is that as the curve moves, all these three planes are changing continuously. Okay, and that is the same as saying all these three vectors are changing continuously. All right, what is changing is only that their directions. The magnitudes are all the same, the handedness still remains the same. What really changes is the directions, and keeping track of the directions is the most important thing. Okay, so now so the first thing that we want to think about is the idea of torsion. So what is geometrically the idea of torsion? See, what is happening is that this osculating plane is, what is the osculating plane? See, it is a plane which contains the tangent, unit tangent, and the principal normal. It contains the circle of curvature and the center of curvature, and what is happening to the curve? It is just coming into the osculating plane and escaping out of that. Okay, that's what is happening. Now you see, because of this, if you change the point a little bit, this osculating plane will wiggle, it will change. Okay, and you can see that if this osculating plane never changed, then the curve will never leave that plane. Okay, that means it will become a plane curve. So somehow the tendency of the curve to jump out of the osculating plane, that should be its torsion. Okay, so that if torsion is 0, it is the same as saying it has no tendency to jump out of its osculating plane. That means it is actually a plane curve sitting in its own osculating plane. For a plane curve, the osculating plane is the plane itself. Okay, and conversely, if the osculating plane is not going to change, the curve is never going to leave the plane, so it is going to be a plane curve of that plane, of that osculating plane. Okay, so what is important is whether the curve is trying to leave the osculating plane, but that is the same as saying whether the osculating planes themselves are changing at that point. Okay, so to understand the tendency of the curve moving out of the osculating plane, which is a tendency for torsion, okay, you have to record how the osculating plane is changing. Okay, but the osculating plane has a nice normal there. There is a binormal there. So to record how the osculating plane is changing, it's enough to just record how the binormal is changing. Okay, so the tendency of the curve at a given point to go out of the osculating plane should be the instantaneous change in the binormal at that point. Okay, the instantaneous change in the binormal should measure the torsion. Okay, so I wrote last time, so that was the thing that I wrote last time. We would like to regard torsion as the rate of change of the binormal. Okay, and the fact is that this change is going to be in a direction parallel to the principal normal. Okay, so so this is something that is that you have to that I want you to think about for a moment. You see, it's like this. see you have the curve like this, okay, then there is a tangent vector, there is unit tangent, there is a unit there is a principal normal, and then this is a binormal, okay. Then you see now, as I already told you, there are 3 planes, but the osculating plane is actually this one, the one that contains the tangent and the normal, okay. See the what could, and if you go to and from this point, if you go to a nearby point, this oscillating plane is going to change, okay, and correspondingly the unit normal to that, which is the binormal, that is going to change, okay. But how this binormal is going to, let us say, move, which direction is it going to move, okay, that is what we are trying to understand, okay. So you can imagine that, you know, so just for the sake of a picture, let me just say the following thing. See, what you could have had is that, you know, it could be rotating like this, which means it's kind of rotating with an axis which is parallel to the normal, okay. Or, you know, it could rotate like this, which means it is rotating with an axis parallel to the tangent, unit tangent direction. And there is one more thing, it could also rotate, so the thing that I can have is you know, something in between this, okay. You can have some rotation that is in between this, all right, and hypothetically you can also have a rotation about, you know, about itself, all right, but in that sense it will not be recorded, because you see, if it is rotating about itself, the direction is the same, the magnitude is also the same, therefore there is no change in that. So this rotating about itself is literally not going to be considered physically. So the only physical considerations are that, you know, this binormal can either, so if this is the tangent, this is the normal, this is the binormal, then a binormal can rotate like this along the tangent direction, which means it will have an axis parallel to the normal, principal normal direction, or it can rotate like this, which means it's rotating along the principal normal direction, but it will have an axis parallel to the tangent direction, axis of rotation, okay. Or it can also be kind of slanted, it can be a mix of these, okay, that is also possible. But the big deal is, what is going to happen is that this binormal is going to only rotate along the direction of the normal. That means it will have an axis of rotation which is parallel to the tangent direction. That means what is happening is, as the curve moves, you see this osculating plane that is rotating about the tangent direction, okay, and the binormal, so the rotation is along the normal direction, parallel to the normal direction, okay. That is what is really going to happen, that's what happens, okay. That's what I have mentioned here. So here is the fact, the change in the binormal is going to be in a direction parallel to that of the principal normal, therefore the change in the binormal will be a scalar times the that direction, and that scalar is going to be written as minus of tau, where tau is the torsion, okay, all right. So in other words, this the magnitude of the torsion is just mod tau is just norm of b hat dot. This is what we wanted. The magnitude of the torsion should capture the instantaneous change in the osculating plane. The instantaneous change in the osculating plane is the same as the instantaneous change in the binormal, which is perpendicular to the osculating plane, and the instantaneous change is dot, and dot is minus d by ds, okay. And the sign, there is a sign, that is because this is a rotation, you need to keep track of which direction of rotation, okay. And all directions of all rotations are all controlled, they have all been fixed because you have already fixed a right-handed triad, okay. So you should remember that. So this is the point, okay. Now we have to prove this fact, okay, and we have to understand this. You have a question? Yeah, so as I told you, the problem is that there are several arguments that you can give or think of as to why you have to forget the sign of curvature, why you have to forget the sign normal in the case of a space curve, whereas you have to remember this, keep track of this when you are on a plane curve. So one of the things that you can see is that from a mathematical point of view, the sign normal and the sign curvature for a plane curve came as adjustments to make sure that the geometric normal always pointed towards the center of curvature. Okay, that was one thing. Then the other thing is, see, there is some interesting thing that's going on when you go from 2 dimensions to 3 dimensions. See, in 2 dimensions, I already told you, if you take 2 circles of the same radius, but you take in one clockwise motion, the other anti-clockwise motion, you cannot move one to the other, superimpose one on the other by a rigid motion. The reason is because the circles themselves can be superimposed on one another because they are same radius. By just a translation, you just have to translate the center of one of the circles onto the other. But even after you do that, on the same circle you will see that the rotations will be opposite. The sense of rotations will be opposite. Okay, and if you want to classify up to rigid motions, the rigid motions keep track of the sense of rotation. So it's clear that in the plane case, if you have 2 circles of the same radius, they are congruent actually. But if you also take the orientations as opposite, then they are not rigid motion equivalent, unless you use a reflection which is not a rigid motion. Okay, but so to keep track of this orientation, you have to bring in the sign curvature. That is one reason. The other reason for sign curvature is when we geometrically wrote down that formula, you see, we had to put the sign to compensate for the case when the sign normal was pointing away from the center of curvature, and you had to give a negative curvature to that case. Okay, you will if you don't consider sign normal and you don't consider sign curvature, you will not get a universal formula for the locus of the center of curvature, which is the evolute of the curve actually. Okay, so these were the reasons we did it. But you see, in 3 dimensions all this changes amazingly. Take the same case, take 2 circles, same radius, and take opposite orientations okay. Now in 3 dimensions what you can do is, there is a rigid motion which can move this to that. In 2 dimensions there is no such. In 3 dimensions there is a rotation. The circle like this, you just rotate it like this, it becomes a circle like this, and this rotation is a rigid motion. So the point is that because you have added an extra dimension, what appeared as a reflection in 2 dimensions has now become a rotation in 3 dimensions, and that is a rigid motion, you see. Therefore in 3 dimensions you have one extra dimension that takes care of the sign of the curvature is taken care of automatically. Okay, but the sign will then be captured by the torsion. Okay, and why the sign of the torsion is important is because you see, when you write a right-handed system, then if you change one of the vectors by a minus sign, the system will become left-handed, right? So the right-handedness of the system necessitates that at least one of the signs are all controlled, they are all interdependent on each other. Okay, and the torsion picks up the sign in the case of space curves. Okay, so that is the idea. All right, now possible, it's possible. So if you continue this argument into 4 dimensions, I am somewhat I'm not sure what is going to happen. Okay, so I wanted to tell you again as part of the story. You see, 4 dimensions is already pretty complicated. So I'll tell you how it's complicated. See, when you do 1 dimensions, you are worried only about functions of 1 variable. Okay, and you have an idea of differential calculus, you have integral calculus. When you have 2 dimensions, you have functions of 2 variable, again you have differential integral calculus. And in 3 dimensions also you have multivariable calculus. But when you go to 4 dimensions, something happens, okay, which is very, very odd. in 3 dimensions or 2 or 1 dimensions, the idea of differentiation or differential calculus is kind of, let us say, rigid, it's fixed. Okay. Whereas if you go to 4 dimensions, okay, there are different ways of doing differentiation. Okay. So this is a very very in a way involved and deep. Okay. In 4 dimensional space, okay, there are different ways of doing differentiation apart from the usual way of differentiation that we do. Okay. The point is, all these different ways of differentiation locally will look the same, but globally they will be different. So there is a theorem to the effect that there are infinitely many non-isomorphic differentiable structures on R4. Okay. So you add one more dimension, okay, even your idea of differentiation is in trouble. You have to fix what kind of differentiation you are going to work with. Okay. And to make matters worse, technically all these methods of differentiation locally will look the same. The moment you do it globally, they will all be different. Okay. So these kind of things which are a mix of topology and calculus, they start coming in. Okay. So it's kind of perplexing. All right. So long as we are in 3D, we are safe. Okay. If you go to 4D, you are in trouble. All right. Yeah. Yeah, we are going to do that. So of course, the purpose of all these things, the purpose of all these things is that you make a definition, okay, and then you make everything analytic. But you must understand that already, you see, in the definition I have already made the principal normal analytic, because what I have done is I have given a formula for it. I say the principal normal is actually, you take the you take the acceleration vector, okay, t cap dot, and then divide by the magnitude of the curvature. So I have given you an analytic expression. Okay. So the point is that we want to characterize torsion. Okay. And the fact is, the change in the torsion, okay, is happening along the direction parallel to the normal, which means the axis is like the tangent direction. Okay. And why is this true? So the point is, here also, for the change in the torsion, there is a turning angle. See, recall when you had a plane curve, how did you get the sine curvature? The sine curvature is the rate of change of the turning angle, and the turning angle is the angle made by the unit tangent vector with a fixed direction. Okay. Now, believe it or not, the torsion will also be, if you define a turning angle for the binormal with respect to a fixed vector, okay, the rate of change of that turning angle will be exactly your torsion. So for the torsion also you have a turning angle. So that, and the interesting thing is that change in the binormal happens along the normal direction. Okay. So let's try to justify this. So the first thing I want to say is, so let us do the following thing. So here is a so fact. So this is let so let me write it like this. Let psi of s be a turning angle for the binormal. Okay. So what does this mean? This means that there is a fixed vector v naught, fixed vector, and I don't, it's not necessary that it is it can be in any direction. I need it to be non-zero. So v naught not equal to 0. It's a fixed vector in some direction. Okay. Okay. Then what you do is that you have the binormal b hat, and b hat is b hat of s, and call this angle as psi of s. Okay. You measure this angle, and measure this angle from that fixed vector. Okay. So that I am keeping track of the sense also. All right. So that is psi of s is the angle from a fixed constant non-zero vector v naught to the direction of b cap. Yes. Okay. Now you have this situation. Now the claim is that so the claim is then that d psi of s by ds is exactly the torsion at s. Okay. So so let me go back and make a small correction here where I should have so I didn't mention it like that. So in this whole business everything is changing with respect to s. So if you want to write it more clearly, I should have written b hat dot of s is equal to minus tau of s times n hat of s. Okay, there is this s that's lurking around everywhere, and remember that this b hat dot of s is nothing but d by ds of b hat of s. This dot is with respect to arc length. Okay, so you suppress the s, but the s is there everywhere. Please remember that. All right. Okay. So the torsion also changes with arc length. At every point, the torsion is different. All right. So, so here is the claim. Now, how does one prove this? So this is one fact. Of course, the other fact is that the change in change in b hat, which is b hat dot, is only happening in a direction parallel to n. Okay, so so let's prove this. It's kind of very easy. You see, first of all, look at the definition. You see, b hat is what? B hat is the the binormal is chosen so that the tangent, the principal normal, and the binormal are right-handed system. So by definition, b hat is t hat cross n hat. By definition. Okay, so if I write it with the arc length in mind, b hat s will be t hat s cross n hat s. Okay. Now what you do is that let's calculate the derivative. Okay, so b hat dot s, okay, this is going to be d by ds of b hat of s, okay, and this will be d by ds of t hat of s cross n hat of s. All right. And now you see, when you do differentiation of a cross product, it's again a product rule, but keep the order carefully, because a cross product is anti-symmetric. If you change the order, you get a minus sign. So this will be, you can verify this quite easily. This is going to be d by ds of t hat of s, the whole cross n hat s, plus t hat of s cross d by ds of n hat of s. If you want, you can write it as vectors and check this. Okay, and cross product of two vectors is given by a matrix, right? You can check this. All right. And but you see, this is what? This is going to be t hat dot s cross n hat s plus t hat s cross n hat dot s. This is what I'm going to get. And mind you, this dot here is d by ds. Okay, but how has n hat s been defined? N hat s has been defined following the plane curve case as 1 by ks into t hat dot of s. This is the definition of n hat. This is how you define the principal normal, right? So because of that, okay, this term will go away, because I will get a n hat t hat dot cross t hat dot is 0, and this 1 by ks is of course a constant. So basically I will get t hat s cross n hat dot s. So this is your b hat dot s. Okay, this is the change in b hat. But what is this direction? What is this direction? You see, t hat, what is the direction of a cross product? It is a unique vector which is perpendicular to both of them, right? And so that they form a right-handed system. Okay. So the first thing I want you to notice is that you see n hat dot is perpendicular to n hat. Why? Because n hat is a unit vector. Okay, since n hat is a unit vector. Why is this true? Because you see n hat is a unit vector, this implies norm n hat is 1. So norm n hat squared is 1, but this is this n hat dot n hat is 1. Okay, this is the dot product. You differentiate, if you apply d by ds, you will get n 2 n hat dot is equal to 0, but this will mean that n hat dot is perpendicular to n hat. So you see, therefore unit vector, a changing unit vector, its derivative is always perpendicular to the original unit vector. Okay, mind you, we needed this to ensure that the acceleration vector of a curve, for a plane curve, is perpendicular to the tangent vector. Okay, we already needed this. That's why we made it unit speed. Constant speed would have been enough, but we made it actually unit speed. All right, we took that constant as 1. All right, so you have this. On the other hand, notice that t is also perpendicular to n hat by definition. The tangent and normal are perpendicular. Okay, because the tangent direction, okay, if you want, even by definition, the tangent direction and the normal direction are perpendicular, because if you want, this normal direction is given by, look at this definition. This definition is 1 by ks t hat dot s, and t hat dot and t hat are again perpendicular because t hat is 1, is norm 1. Okay, so I'll just write it here. Let me just write it here so that let me write here t hat perpendicular to t hat dot, since norm t hat is 1. Same reason, whenever you differentiate a unit vector, its derivative is perpendicular to the unit vector. All right, so now watch, see b hat dot, okay, it's a product of two unit vectors. It's a product of two vectors. Okay, it's a cross product of two vectors, so it's perpendicular to both of them. But there is one candidate. This n hat is perpendicular, is the vector that's perpendicular to both n hat dot and t hat. Okay, therefore the moral of the story is that b hat dot must be parallel to n hat. That means they should differ by a scalar. Therefore b hat dot is equal to minus tau n hat. There's a scalar, this is a scalar. Okay, and we put a minus sign. I will explain why. Okay, the reason for that minus sign is also geometric. Okay, you can also take it as a convention, and there is also a geometric reason for that. Okay, so, and this scalar involved is the negative of the torsion. So what does this simple calculation tell you? What does it tell you? It tells you that the change in b hat, okay, which is change in the binormal, which is b hat dot, that is instantaneous change in the binormal with respect to s, b hat dot s, that is scalar times n hat. So the change in the binormal happens along the normal direction with the axis as the tangent direction. So you see, you have the tangent like this, you have the normal like this, and you have the binormal. The binormal change is like this. The binormal change is happening in this direction, in the normal direction, and it's like rotating about the tangent direction. Okay, so that is a fact that I told you last time. All right, then so that is one thing. Then I wanted to come to this fact that the rate of change of the turning angle is also the torsion. Okay, and how does one see that? So you see, if you look at it, so let me draw one more picture. So you see, you have this. So you have this curve. Let me put something else. So you have this curve, and you have the tangent. So this is gamma s. This is gamma dot of s, which is t hat s, this is the tangent, then you have the that is the normal, principal normal, and then there is the binormal. And then there is some vector v naught, constant vector, and if you draw that vector here, say v naught here, okay, then this angle from v naught to b hat, this angle is your psi of s, okay, and the claim is that d psi of s by ds, this rate of change of this turning angle is exactly the torsion, okay, that is the claim. All right. Now, what I want you to understand is that, you see, let me first make the following statement. So I'm just trying to draw a nice picture. So let me draw it like this. So this is my b hat s, this is my t hat s, and this is my n hat s, okay. Let me redraw this, okay, and remember this is 90, this is also 90, and this is also 90, okay, and you have this v naught, some fixed vector, okay. Of all these things, you see this v naught is fixed and this angle is psi s, okay. Now how do you get this angle? The angle between two vectors is given by a dot product. So psi of s is going to be nothing but b hat of s dot v naught. This will give me psi s, okay, all right, and of course I should write cosine, okay, and of course I should have also, see, the dot product is what is the cosine of the angle, and then you should also take the magnitudes of the vectors, and b cap is a unit vector, magnitude 1. I will also make this assumption that v naught is also a unit vector, okay. So I will say if v naught norm v naught is 1, so I put this, okay. Otherwise I have to put the norm of v naught in the denominator, okay, in the right side. So you take v naught to be a unit vector, fixed unit vector, all right, then this is correct. Now how do I get the rate of change? I have to differentiate, okay, but I will tell you something here. I will make use of the following fact. See the change in the b is only going to happen along the normal direction, okay. Therefore what is the angle that actually matters is you project this v naught onto this unit vector onto this normal plane, okay. You will get this vector v naught tilde of s, okay, that is the projection of v naught onto the normal plane, and then this angle, if I call it as psi tilde of s, okay, I want you to understand that this is also the dot product of v naught tilde and b cap is the same as the dot product of v naught and b cap. The reason is because this v naught will have one component along the tangent direction, the remaining part will be the projection onto the normal plane, okay. See, so let us do the following thing. Let me first differentiate this. If I differentiate this with respect to s, I will get minus sine psi s d psi s by ds is equal to, differentiate the right side, mind you v naught is a constant vector, so what I will get is I will get b cap dot s dot v naught. This is what I will get. If I differentiate, this is what I will get, okay. But now you see, now watch carefully, this b cap dot is in which direction? It's in the n direction, it's parallel to n, okay. So the dot product of b cap dot with v naught will be the same as dot product of b cap dot with v naught tilde, because the dot product with the other component which is along the tangent direction will be 0. Okay. So this, see, if I calculate this on both sides, and you will get d psi s by ds is equal to tau. Okay. So there is only a little bit of confusion that, you know, even though v naught is a unit vector pointing in one direction, for all practical purposes you could have taken v, instead of v naught cap, you could have taken v naught tilde itself. You could have just taken a unit vector, you could have taken its projection on the normal plane. Okay, because the component along the tangent direction will get killed because of the dot with the n cap. Okay, and then therefore the torsion becomes the rate of change of a turning angle. Okay, so this I will again redo this next time. Okay, so therefore just like the, you know, unit tangent vector has a turning angle, the binormal, which is unit vector, that also has a turning angle, and the rate of change of the turning angle is exactly the torsion. And you see the sign, had you put plus tau, you would have got a minus here. If you had put here plus tau, here you would have got a minus, and your torsion would have become negative rate of change of the turning angle. Okay, so now you see why there is a mathematical justification why you put a minus sign. Okay, not only that, there is also physical justification why this minus sign has to come if you look at helical motion. Okay, so I will explain that. Okay, so this is just to tell you that torsion is also something that can be quantified by a turning angle. Okay, so I will redo this. Okay, let's stop here for the day. Yeah.